Hi, Gerd. Sorry
Hello,
about
how are
that.
you?
I went outside and I almost forgot.
Okay, let's see. I have the right speaker. I have the right microphone. Should be all good.
Hi guys.
Hi, Stephen. How are you?
Good, good. Hi, Laurie.
All right. Let me see if I can. Laurie, can you give me a screen share?
Oh, yes.
Okay. Let's share an application. And yeah, the one thing that I don't like about Zoom is really, I mean, okay, I'm sharing my screen now, but everything else, all the other controls from Zoom disappear, and which is okay. I mean, but like in Whereby, for example, that I use, at least I can still see people, and yeah, that's okay. Just moaning. Okay, let's see. We had, yeah, I haven't checked as of this afternoon, but when I checked this morning, there were 2 questions.
Oh, good.
We'll go over them. And I have a few prepared notes, and there's plenty of things going on. And so, okay. And then,
So we had Elena register to join us.
oh, okay. She must be bored. How is the weather where you are, Stephen? Stephen, you're muted, but that's okay. Can you still hear me, Laurie?
I can hear you.
Okay, because I don't know what happened to Stephen.
Oh, he's putting in headphones, so maybe that tells us something.
Okay, maybe he
No, the track lights. I have track lights up there, and then I
Oh,
just realized
well, no,
because I'm turning towards the window. I mean, the windows are in the back, right?
Well, Gerd just asked you how the weather was, and then I thought that perhaps you couldn't see or you couldn't hear us, and then I saw you putting in headphones. So,
right.
all of that.
And but it's warm.
Okay, I'll start the timer for 25 minutes. And then, yeah, I'll start. You can, I mean, I assume you're letting people in. We will just get going in a few seconds, in 3 seconds, 2 seconds. Okay, it's 1 o'clock again. Welcome to this HDF clinic, and thanks for submitting questions. When I checked at 9 o'clock this morning, there were 2 questions in the Google Doc, and I have not checked since, but if there's time, I'll check once more, or we'll come back to any additional questions next time. And then there might be questions live from the audience, which is perfectly fine and invited. And but we also have a few announcements, and then if there's time, go over some interesting forum posts. Question number 1, someone was asking, is there a limit on array size if I save an array as an attribute of a data set? And then part 2 of that question, in terms of the performance, is there any consequence if I save a large amount of data into an attribute? Great question. Let's do it one by one. Size limit? No, the answer is no. In newer versions of HDF5, that is 1.8x, x would be 22 as of now, and higher versions of HDF5, there is no limitation on the size of the value. I think this is what the question here is. If you think of an attribute as something that has a name, a data type, and then a shape, if it's multidimensional, it doesn't have to be scalar. And then the size of that value, that typically multidimensional array that represents that value, is there a size limitation on that? And the answer is no. There will be an HTML version of this available later. I hyperlinked here the one of the knowledge base articles that discusses this question, sort of what limits are there in HDF5 as sizes and so forth are concerned. And that also discusses that question of attributes, and it basically says what I'm saying here. So that's number one, no size limitations in newer versions, that is 1.8 and later on the value, on the size of that value of that attribute. Second question, in terms of the performance, is there a consequence if you save such large amounts of data into an attribute? I would say it depends, and it depends in the sense that what you mean by performance. And but before I go there, so if performance for you just means throughput, I would say by and large, no, it's not going to be any faster or any slower than a data set, but there are some interesting restrictions that apply to attributes that do not apply to data sets that might change your opinion on that. First of all, I would point out that attributes traditionally have a different function, perform a different function as opposed to data sets in HDF5. They are sort of, from a data model perspective, their primary function is that they decorate other objects. People use them frequently to represent what I would call application metadata. And they are also, unlike data sets, treated as atomic units, in the sense that, like in the simplest case, you can think of an attribute as a key value pair that you can sort of attach or tag onto another HDF object. The value is treated in an atomic fashion, in the sense that whether you want it or not, you have to either write the entire value or you have to read the entire value. This capability that is available with data sets that we call partial I/O, that you can do selections, hyperslab selections and so forth, or that if you have a compound type that you can read just a particular field or a subset of fields, that capability is not available with attributes. And thirdly, if you are working with data sets, then you have several layout options, in the sense that for data sets, for example, we have this concept of a compact data set, of a contiguous data set, of a chunk data set, of a virtual data set, and so forth. All of these things are not available with attributes. In particular, compression won't be an option with attributes. So especially if your attribute is large and the data is compressible, that option won't be available to you with an attribute. And again, to me, the most limiting factor is really they are atomic in the sense, and if they are large, that means you are committing to, by representing your data item as an attribute, you are committing to reading and writing the entire thing all the time. As far as performance goes, I'm in no position to have any conclusion here, but those are the limitations, and to me they are performance limitations beyond just performance. As far as pure throughput is concerned, I wouldn't think that there is a tremendous difference or a substantial enough difference that would make me consider to go one way or another. I think it's these usability, which for me is another aspect of performance, constraints that would drive my decision one way or the other. And I hope that answers the question. If the person who asked that question is in the audience, let me know if that answers your question, or if I was unclear. Or somebody has additional comments, feel free to jump in. Okay. Then maybe I'll go on to the second question. The question is regarding HDF5 I/O performance. Compare saving data into a large array in one data set versus saving data into several smaller arrays and in several data sets. Are there any consequences in terms of performance? Will there be a sweet spot for best performance, or any tricks that we could share that make reading or writing faster? Parallel I/O might be a consideration, but then the person says that let's stay away from that for now. So it's really the question of what can be done, what could be done to make this as performant as possible. Now, so if I simplify that question, the question is really one large data set versus many small data sets, which is faster? And again, I'm not trying to be evasive here. It really depends. There is sort of a bigger question. And I will, we can still after this have a discussion where we say, okay, we are not interested in that, or we are, but let's first look at the big picture here. My first question would be is really, how do you access the data? And what I mean by that is, for example, do you always read or write the entire array? So for example, when you read it back, are you really reading it back in its entirety and in the order that it was written? Or are you jumping around, or are you selecting just blocks of it? So I forgot a slash here, let me throw that in there. The next question would be also, is that that data set, or these multiple small data sets, are they what we will call warm, in the sense, do you write them once and then you read them back many times, as this is a very common use case? But if you change it, how do you change it, and how frequently do you change it? So by how do you change it? I mean, are you just updating, or would you be just updating individual values in the data set, but the overall shape? And by that I mean, let's say it's a two-dimensional data set, n by m, and n and m don't really change, but you are updating individual values? Or is it the case that either n or m or both are actually growing over time, or shrinking? Or so that would be a question of how they change. And then of course the question, how frequently does that happen? Another consideration would be how compressible is the data? If the data is highly compressible, we would hope that we can utilize for the data a good compression algorithm. An alternative, and I just throw that in here, if some of you attended one of our recent webinars that was dedicated to sort of what we call programmable data sets, or HDF5 UDF, a very interesting project. The question you could ask, do you need to store data at all? If you have a generator, a function that could generate your data, well then there's actually no need at all to store any data. You could just store the generating function that in the HDF5 UDF project can be in Python, and C, C++, or in Lua. And so you have some choice of language there. So the question would be, do you really need to store a lot of data? Next would be, when you say performance, what does that mean to you, and how do you measure it? So in the previous question, we talked about there is typically a lot more to performance rather than throughput. It's okay if it's throughput, it's going to be throughput, and we will talk about specifically throughput, but there's typically a lot more to this type of optimization problem, you might say, than just one number or one thing. The question would be also in the context of a bigger application. I mean, obviously, an application that just writes one large or split across multiple data sets data is probably not very interesting. So there is probably more going on here. And then the question would be, well, what percentage or what fraction of the total runtime do you really spend in an I/O operation or in I/O operations if you do that iteratively in some kind of time loop or sequence?
Apologize, Gerd, I can't hear you.
To either strong scaling or weak scaling, where you either scale the amount that each process writes that grows with the number of processes. That would be a weak scaling approach, or a strong scaling approach where the amount of data that you are writing is pretty much fixed. So the more processes you throw at that, each individual process will typically be writing less and less data. And then assuming throughput is the measure, you are only interested in megabytes per second or however you want to measure that. The first thing would be to look at creating what I would call a baseline for your target system. So that would be take one of the benchmarks like FIO or IOR, and that will give you some numbers. So you typically want to run that with, like, do random writes and reads with 4 kilobyte blocks, with 1 megabyte blocks, and so forth, just to get a feel for what your subsystem is capable of doing. And then, of course, if that's your target, your goal is really to saturate this given I/O subsystem. As a side note, I would say the question is, of course, is that a system that's dedicated to this application at your disposition, or are there other activities going on? Because all of that then feeds into, you can do the perfect job in terms of optimizing throughput, but you may in the end not see very much of that because there's a lot of noise and interference and concurrent activity, so that you might have spent a lot of time and diligence and effort, but it doesn't really pay off. And of course, you also want to keep an open mind about let's assume this is a collaborative effort, or you are sharing this data with colleagues, with collaborators, then do you need to support other systems? Because you might do a stellar job on tuning this and optimizing this for a particular setup, maybe for a particular memory hierarchy, cache sizes and whatnot. But then the moment you move this to another system, your results are not exactly that great. But then again, you don't want to fall into this trap that you are optimizing something highly for just a very specific set of circumstances that then no longer apply once you move elsewhere. And then are you the only user, or are there other users? And then, of course, what's the future? What the system that you will have access to or available to you? If you work in the cloud, for example, I don't know how many new instances come out from the different cloud providers. but then also in a year and 2 years, how will the landscape change? And then in the end, the big question is always, what's the budget? What's the budget in terms of expertise and manpower and time that you can sink into that? And then, yeah, how much money whoever sponsors this effort, how much resources do you have available? So this is sort of the larger context. Now, if for I can pause here if the person who asked this question is in attendance, then you can comment. I invite you to comment. But if not, then I can say a few more specific things about the throughput optimization. If that's the end all and be all, fine. There are some relatively simple things that you can do. Is the person who asked that question around? No? Okay. Well, then I can just be brief. But what I can say is, so let's assume you're not worried about sharing this with others. This is your dedicated system. There's no interference with other things. Let's also assume it's something like write once, read many. We are always reading the data in the order that they were written. And because all of these things will complicate matters, then that's really our goal can then only be whatever FIO or IOR tells us. That's the performance. Once we achieve that performance in terms of throughput, that's what the system is capable of doing. And that's the end of the story. Now, I'm going to, for a moment, bypass the question of compression, because that skews that a little bit, because reading 100 megabyte of compressed data that then uncompresses into a gigabyte is different from reading 1 gigabyte, although if you read contiguously 1 gigabyte and so forth on a pretty powerful IO system is going to be very fast, but still with modern CPUs and sort of multi-threaded compression and so forth, you can be pretty good with applying compression and then spending more compute cycles to decompress or compress. But I'm going to sidestep for now. So let's assume this is a pure throughput problem. I think the simplest thing to do is basically take a benchmark like H5perf, for example, in addition to FIO and IOR, where you can actually run HDF5 with different interfaces, but you can actually get a direct comparison between the POSIX without any HDF5, the POSIX throughput without any HDF5, and then the throughput with HDF5. And if those numbers are pretty much identical, then I would assume that the performance for your application is as good as it can be. The only room for improvement that might remain is that, let's say, you are getting only 50%. So FIO says you can get 2 gigabytes per second. And of course, typically there is a certain factor between read and write performance. Writes tend to be typically a little slower, maybe just 2/3 down to a half, depending on circumstances of the read throughput. Let's say, but let's just stick even for simplicity with just writes. So we can write according to some of these benchmarks at 2 gigabytes per second, but FIO, but H5perf says I'm reading only with 1 gig. I'm writing. I'm sorry, with only 1 gigabyte per second. So that would mean that we are leaving 1 gigabyte 50% on the table. And the obvious way to fix that might be, for example, to use a second control flow, either a second process or a second thread to do that I/O. And if it's a second process, you could do that with MPI. But if you don't want to go down the MPI path, what you could do is, in the simplest case, we run with a contiguous data set, and you can allocate that data set early when you create it in the file, so you know exactly the layout in the file of that data set. And then you can just spawn 2 threads and basically write directly into the file. And if you are lucky, your IO subsystem will be able to sort of sustain both simultaneous writes, and that will be as good as it gets. Now, on the downside, of course, you can ask yourself, what is the increase in code complexity? Because when we talk about performance, it's always, at the throughput level, it looks simple and it's a purely technical problem. But looking at the bigger picture, coming back to the budget, how much time, effort, and so forth do you really want to invest in that? Because once you go to the next system, do you want to modularize your code for more cores, for more threads, for more concurrency? How likely is it that your next system will have more headroom to utilize for these IO operations? And then again, going back to the entire application, if you're spending less than 1% of your application run in IO, why would you spend any time at all in sort of tweaking that? If you have scalability problems, that's a different story. But then again, now we are making it more general, more complex. So that's why I believe, unfortunately, there are no simple answers here. It really depends very much on your boundary conditions, so to speak, on your constraints, and then you can work within those constraints and find a good solution, maybe even close to optimal solution. Maybe you can prove to yourself that it's optimal under the circumstances. Okay, that was question number 2, and we have a few minutes left. So unless there are questions, so I'm going to pause here. Are there any other questions? No? Okay. Then I will come back to 2 things, some announcements and then some interesting activity on the forum. The announcements last week were that the H5Py project released their version 3.2. The highlights, I hyperlink the release notes here. There is support now for the HDF5S3 read-only virtual file driver, thanks to this gentleman. And however, unfortunately, a pip install of version 3.2 is not going to do the trick. You will, as is pointed out in the release notes, and there are instructions how to build H5Py from source, because with the S3 driver, there is an additional dependence on libcurl, which I believe is not sort of part of the default distribution. And so you have to bring in libcurl. And okay. And minimum Python version is 3.7 now, no longer. Okay, I think the release notes state they don't test it anymore with 3.6 and earlier. It may very well work, but no guarantees. Your mileage may vary. There was also an interesting bug fix mentioned in the release notes. It had to do with writing variable length arrays of fixed length strings. If that affected you, good news, that was fixed in this release. And there are a few other things, but I just sort of picked out the things that caught my eye. There is a BOF that's pretty much the end of the month, but there will be an HDF5 community BOF at the Exascale Computing community BOF days, March 30. I think it's a 2-day event, March 30th and April 1st, and you should go there. if you are interested in the ECP program, the activities there that include HDF5, but there are a lot of other activities, I definitely recommend you go there and check this out. But yeah, the HDF5 off is on March 30th at 3 p.m. Eastern time. And you can register and find more information there. Okay, we have 4 minutes. I'm trying to make this quick here. There were 4 interesting discussions. One had to do with the object header size. Not quite. Question number 1 was asking about size limitations for attributes, and there is not a direct connection, but an indirect connection between that question 1 and the issue that this person encountered here, which was that the person created a large compound type with hundreds of fields, and then always after a while, after adding fields and fields and fields, they got this error message where the library was basically complaining about an object header message that is too large. It turns out that this issue is actually a good old friend, if you want to call it that. It was first reported over 10 years ago, and the root cause of this issue is basically it's deep down in the file format. And I pointed out these sections here in the file format specification, which might be, if you for the longest time sort of felt intimidated by looking at the file format specification, I don't think it's that at all. And here are some pointers where you might start reading in the file format specification, and it's actually not that difficult. The case is that a data type is represented as a so-called header message. So the things that we call objects in HDF5, the data sets, the groups, and so forth, you can think of them, they are not just simple structs, but they are pretty much patterns of messages that the library manages. And one of the message types in these message patterns for a data set, but also for an attribute, is what's called a data type message that basically indicates what the type, if it's nested or if it's just atomic, and in the case of a compound type, for example, what the names of the fields are and what in turn their type is, and so forth. And the reality is that in the file format specification as it stands, the size, there are 2 bytes set aside to specify the size of such a header message. And in 2 bytes, the largest unsigned integer that you can express in 2 bytes gives you up to 64 kilobytes. And that's the reason. And so when you start creating very large compound data types, you are basically, the clock starts ticking or the counter starts ticking, and you're running against these 64 kilobytes for that one message that describes that data type. And at some point you will just run out of space. Now, this can be fixed, of course, through a file format update. But obviously, these file format updates, when we do them at all, we do them between major releases, between, let's say, 1.8 and 1.10, 1.10 and 1.12. And you might say, well, we had 10 years, we had plenty of time to fix that. Well, it wasn't really a priority. And of course, the amount of testing and engineering that goes into making sure that a change in the file format, as small as it may seem, is sound, is very costly. And that's where we have to sort of make a decision and say, well, how important is it really for our users to have, for example, compound types that have hundreds of members? And that takes us back to, what's the use case? The use case could be really to say you have hundreds of fields, but then again, as far as performance goes, to come back to performance, that's you are really reading them and writing them together all the time. Otherwise, your performance will suffer. And you are also getting outside the mainstream here, because not too many tools will actually be able to handle such large types. And it's better to do a divide and conquer approach and break things up. And I see time is up, but hey, it's half an hour every week. Come back next week. If there are more questions, I will post the write-up to these other questions, and then you can decide if you're interested in those issues, follow up. And thank you for coming, and I invite you to come back next week. Thank you. Bye.